Okay.
Okay, welcome everyone for the third and final lecture of Shu-Heng's lectures on anomalies. Please, Shu-Heng.
All right, thank you. All right, so let me briefly say a little bit about what we discussed yesterday. So yesterday we started talking about Z2 global symmetries in 1+1D and how to gauge it if we could. So the simplest example is to consider the Ising CFT. In the Ising CFT, there's a Z2 global symmetry, and therefore we can divide our Hilbert space of local operators into the Z2 even and Z2 odd sectors. In the case of Ising, these are the identity and the thermal operator, and the Z2 odd operator is the order operator. But more interestingly, we also consider twisted sector of the Ising CFT twisted by the Z2. And then we should also include the disorder operator and the fermions. Under gauging the Z2, we don't lose any operators. Rather, the Z2 odd operator is projected out and demoted to the twisted sector. On the other hand, the Z2 even twisted sector, say, got promoted to become the new Z2 odd untwisted sector state. So what Z2 gauging does in 1+1D is to exchange these two sectors. Some of them got demoted, some other got promoted. The question we left out yesterday was that in this two-step procedure of gauging a Z2 symmetry, in the first step, we throw away some state. There's no problem in that step. You just throw away something. But the second step looks more dubious, where we introduce some local operator, and they used to be some non-local operator attached to strings. But how do we know the operators we promoted or we liberate from the twisted sectors have integer Lorentz space? In the case of Ising, that's the disorder operator, and that's consistent. But that's not always the case. And that's where we will run into anomaly. So I'm going to go through some Z2 symmetries in the free boson CFT. In this case, it's a free CFT. We can really solve everything, including the twisted sector. And we will see that for some Z2s, the twisted sector state will have no integer spins operators, and therefore that Z2 cannot be gauged because we do not know how to do the second step, and that signals the anomaly. So let's start with the one of the Z2 there. So recall that the free boson CFT has a U1 momentum symmetry and a U1 winding symmetry, which we discussed extensively yesterday. And there's a mixed 't-Hooft anomaly between them. So before I go into any details, the answer is relatively clear. If you look at the Z2 subgroup of the U1 momentum symmetry, there's no anomaly. If you look at the Z2 subgroup of the winding symmetry, there's no anomaly. But if you look at the Z2 subgroup of the diagonal U1, there will be an anomaly. Now let's try to see that more explicitly.
So there may be anomaly, but it's not guaranteed that it will be.
It's not guaranteed, but I will show that they will. Yeah, in general, it could be that I have a bigger group with some anomaly. But if I look at a smaller subgroup, the anomaly trivializes. That happens every day, indeed. But for this particular, in this particular dimensions and for this particular anomaly, the Z2 is actually big enough for there to be an anomaly for itself.
Okay.
And we will demonstrate that very explicitly. Okay, so let's start with the Z2 subgroup of the momentum symmetry. Recall that the momentum U1 shifts phi by a phase. The Z2 subgroup is generated by shifting phi by pi. So we're only shifting phi halfway through the circle. All right, so let's try to study the Z2 twisted sector of this Z2 momentum symmetry, which will be denoted in blue. As I said, this is a, okay, let me see, okay. This is a free theory, so we should be able to solve everything. Before we actually look into the twisted sector state of this Z2 momentum symmetry, let's first recall some operators in the untwisted sector. So recall that in the lecture from yesterday, we talked about winding configuration, which are states in the untwisted sector. The winding configurations are labeled by integer winding number. This classical winding configuration then corresponds to a quantum mechanical winding state, and by the operator state correspondence, it is mapped to a local winding operator. Here, the adjective local means that this is an operator living in the untwisted sector. And the winding operator is given by this expression with integer winding number. That's important. Now, what about the twisted sector? We now insert the twist as we go along the spatial S1 direction. And the twist is to shift phi by pi. So now a winding configuration in this twisted sector no longer has integer winding number, but there's an important 1/2 shift here. This is because if you take this configuration, you shift x by the circumference of the spatial circle, then you get an ordinary 2 pi periodicity, but you get an additional shift. And this additional piece is precisely what the Z2 momentum twist is doing. So what have we done? We identify a classical configuration in the twisted sector of the Z2 momentum symmetry, and that will give rise to a quantum mechanical state. More generally, so via the operator state correspondence, this classical configuration then corresponds to a non-local winding operator attached to the Z2 momentum branch cut. And it carries a half integral winding number. So let's recap. The fact that the momentum Z2 twist results in a half integral winding charge is another manifestation of the mixed anomaly between the two U1. So what it does is you use the momentum Z2 to twist, and that makes the winding half integral. Vice versa, if you do a winding Z2 twist, you will make the momentum charge half integral. So this is the operator we talk about. It's a non-local operator. It's attached to a Z2 branch cut. It has a half integral winding charge. And of course, you can always stress it with a local operator, an ordinary momentum operator. So the most general possible operator in the twisted sector by the Z2 momentum symmetry look like this. It has integer momentum, but half integer winding. All right, so yesterday we have a homework problem, which was to work out the spin, the conformal weight of this local operator O and W. And let me remind you that one of the result is that the Lorentz spin S, namely H minus H bar for this operator is given by N times W. And it's not hard to convince yourself that this formula extends to operators living at the end of a branch cut. But now the winding number is half integral. So we conclude that the Lorentz spin of these operators with strings attached is given by this. It's an integer times a half integer. And that belongs to this set. So the final spin can be an integer or a half integer. In particular, some of these operators have integer Lorentz spins. And that means this Z2 is actually non-anomalous. And when we gauge this Z2 momentum symmetry subgroup, we liberate the integer spin operators. More specifically, those are the operators with even momentum charge and half integral winding charge. They have integer spins, and they can be liberated from the Z2 branch cut. And we leave the other half integral spin operator in the twisted sector. So this will be the analog of the disorder operator in the case of Ising. And the half integer spin operators are the analog of the free fermions. Excuse me. And similarly, the winding Z2 symmetry is also non-anomalous and can be gauged. In fact, when you gauge this, either of this to Z2, what it does is to change the radius by a factor of 2. Now let's look at the anomalous Z2, which is the Z2 subgroup of the diagonal U1. The diagonal U1 is anomalous. So now we have a twist both by the momentum and the winding. It is therefore easy to see that what that does is to make both the momentum charge and the winding charge both half integral. So now in this purple twisted sector, the operators look like this, and its spin is given by this formula. Very importantly, this is never an integer. So no operator in this purple twisted sector has integer spin. So no operator is qualified to be liberated from the Z2 diagonal branch cut. They don't deserve the promotion to be a local operator. And therefore, we cannot gauge this diagonal Z2. And this is the reason why this diagonal Z2 is anomalous. So let me just summarize. In the 1 plus 1D free boson, we can look at this 3 Z2s. The momentum Z2 subgroup is not anomalous. It can be gauged. The twisted sector operators have integer momentum charge and half integer winding charge. Its spin is given by this formula. Some of them have integer spins and therefore can be gauged. And vice versa for the winding. For the diagonal Z2, no operators have integer spins, and the spins are given by this set, and therefore it cannot be gauged. So we demonstrated this in the case of free boson, where we can solve everything.
Can I ask a question, Shu-Heng?
Yeah.
So the fact that in the last case no operators could be freed of the cut, yeah, this shows clearly that something is wrong. But in the first two cases, you say, okay, there are some operators with integer spin, so they can be freed.
Yeah.
But how do we know that that's enough? That the amount of operators that can be freed is enough to restore the the modular invariance? Is there some check to be made, or is it?
So indeed, this is only a necessary condition. Yeah.
Okay.
So to check it fully, for example, we can check it at the level of the torus partition function.
Yeah.
So this is the gauged theory, and its torus partition function is given by this. This comes from the Z2E, sorry. This comes from the Z2 even untwisted sector state. This comes from the Z2 even twisted sector state. And another consistency check at the level of the torus partition function is that you can see that the right-hand side is manifestly modular invariant, because as you do S, you just exchange these two terms. Mm-hmm. And the sphere 4-point crossing is manifestly preserved. Or maybe at least for the untwisted sector. For the twisted sector, it might require some work, but I think that can also be done. And then you probably have to check the torus 1 point. And after checking that, it's all done. But you are right, indeed. I'm just I'm not giving the full proof, but I'm just trying to provide some necessary condition to see, to diagnose some problem. But at least at the level of the torus 0-point partition function, the modular invariance is quite clear if we follow the two-step procedure. Okay.
That's good.
So what is the necessary condition that we can understand from this table?
Oh, I'm just saying that the fact that the momentum Z2 symmetry, its twisted sector have integer spins is a necessary condition.
There must be at least one operator in the twisted sector with integer spin. Is that a necessary condition for you to be able to gauge it?
Actually, let me get to the next slide. I'm going to announce the result. I think we'll address this more properly. So above, I only did the free boson case. But in fact, more generally, using the machinery of topological defect lines, you can show that the Lorentz spin of a Z2 twisted sector obey the following spin selection rule. When the Z2 is non-anomalous, the spin has to be of this form. When it's anomalous, it has to be of this form. And you can show that using the machinery of topological line that in this case, these are the only two cases. And in this case, you can gauge it and get a consistent theory.
I see. But there's some more words to be said here.
Absolutely, absolutely. Yeah. So for example, one of the things to check the torus partition function. And this is indeed using the topological line. This cuts are exactly the topological line. Okay. So this is a more general result. I'm not proving that right now. It's actually an interesting proof. You can see this paper for the proof. It's using some general property of the Z2 branch cut. But in any case, we demonstrated that in the case of free boson, and I hope that's convincing enough. So we have a table for gauging a non-anomalous Z2 in the case of Ising that we talk a lot about. We have 4 different sectors, untwisted, twisted sector, Z2 even, Z2 odd. But this is for a non-anomalous Z2. What about for anomalous Z2? What can we say? So for that, let's talk about a simple example, the SU2 at level 1 WZW model. This sounds like a fancy name, but it's actually just our free boson CFT at a particular radius. More specifically, if you remember from the first lecture, we talk about T-duality. And the consequences, one consequence of the T-duality is that the moduli is the conformal manifold, at least part of it, look as follow. It starts from 1 and go all the way to infinity. And the point R is identified with 1 over R. And the SU2 WZW model is exactly at this endpoint, well, of the moduli space. Oh, anyway, this is just a particular point of the free boson CFT that's easier to analyze. And as we discussed in lecture 1, at this point, the free boson CFT is rational, and the extended chiral algebra is the SU2 times SU2 Kac-Moody algebra. What are the operators? So in the untwisted sectors, we have the vacuum module for the SU2 current algebra. And then we have a spin 1/2 module, with spin, by spin, I mean the SU2 spin. And its conformal weights are given by this. It's a scalar operator. This is a Z2 even operator. This is a Z2 odd operator. They're all local, they're both local operators, so their Lorentz spins are integers. In the twisted sectors, there are 2 modules. One of them has 1/4, 0, the other has 0, 1/4. They have their spin is not an integer, rather they take this formula, and that's consistent with this spin selection rule that we saw. But notice that I didn't put Z2 even or Z2 odd here. While it's meaningful to say this operator is Z2 even and this operator is Z2 odd, it doesn't mean anything to say this operator is Z2 even or odd. In fact, this operator, in a sense, carries fractional Z2 charge. In a sense, it carries a Z4 charge. But I'm not going into the detail of that. In any case, for anomalous Z2, I should have write that more explicitly. For the anomalous Z2, this is the purple anomalous Z2 that we discussed above in this particular radius. You can group the operators into these 4 sectors again. Okay, so that's our first encounter of the Z2 anomaly. Oops. Now let's try to understand this anomaly from the 2+1D SPT point of view. So recall that for every anomaly, for the anomaly we talk about today, there's always a SPT or invertible field theory in 1 dimension higher that implements the anomaly inflow mechanism. So let's ask, what's the 2+1D invertible field theory for this Z2 anomaly? It's actually easy to derive that. So in the case of free boson, we know that the SPT is given by this off-diagonal Chern-Simons term. Now, if we only look at the diagonal one, that's easy. We just equate the 2 background gauge field, replace their color by purple, where the purple A is the diagonal U1 background gauge field. This is just a U1 level 1 Chern-Simons term. Sorry, U1 level 2, I misspoke. How do we get the SPT for the Z2 subgroup of this U1 symmetry? Here, this A is a U1 gauge field. To make it Z2, all you have to do is to introduce a dynamical U1 gauge field, which I call little b, and add this term. Intuitively, what this term is doing is that you can integrate out the little b and force the all the Z2, the holonomy of 2A to be trivial. And that has the effect of reducing the U1 group to Z2. It's like a Higgs mechanism, except for the fact that this A is a classical field. So I use a lowercase letter for the dynamical field, which we integrate over, and the uppercase for the classical field. This is the answer for the anomalous Z2 SPT. It is the continuum description of the Levin-Ku model in the condensed matter physics. That's the lattice model for this Z2 SPT. So the picture we have is the following. On this 1+1D boundary, we can have a CFT with a Z2 global symmetry. There are 2 cases to discuss. The first case is when the Z2 is non-anomalous. For example, you can take it to be Ising CFT. In the second case, you can the Z2 is anomalous, which, for example, you can take it to be the SU to a level 1 WZW model. The anomalous Z2 is the purple diagonal Z2 we talk about. In terms of the SU2 Kac-Moody algebra, that's the center Z2 of the SU to a level 1. In both cases, we can couple the Z2 symmetry to a 2+1D bulk classical field theory. In this case, it's a trivial SPT. In this other case, it's a non-trivial SPT. The difference is this twist. So far, the capital A is still classical. We're not gauging anything. We just couple the 1+1D CFT to some invertible field theory in the bulk.
Yeah, I guess it's not really clear to me. I mean, you write the symbols BDA, yeah, but for me, this means nothing really. I don't know how to manipulate this correctly.
Okay.
Let me see. I
yeah.
might be able to sketch that. Oh, I think I might be able to sketch that. Yeah. Well, the easiest the one thing to notice is that, the equation of motion of B is 2dA equals to 0.
Yeah.
So intuitively, the 2 fixes the U1 to Z2. And there's a more precise way to say that. And actually, in 2 slides, I might have more to say.
Okay.
Yeah. So this is just SPT. And next, we can promote the background gauge field A to be dynamical. In other words, we can gauge this Z2. For this one, you don't need the bulk to gauge because it's non-anomalous. For this one, you cannot gauge it in 1 plus 1D because by definition it's anomalous. But you can gauge it once you couple to a 2 plus 1D SPT. Then the system is not 1 plus 1D, but a couple 2 plus 1D, 1 plus 1D system. And then you can gauge the Z2 altogether. And that's what we are going to talk about. So what did I do? The only thing I did is to write a capital A in terms of little a. But now the bulk is not an SPT. It's a dynamical Z2 gauge theory. In the other case, it's a twisted Z2 gauge theory. So now coming back to Slava's question, how do we think about this Z2 gauge theory? Why is this the right description? So this is an off-diagonal Chern-Simons term involving 2 U1 gauge field, E and little a. There's no local operator in this theory because the equation of motion tells you dA equals to dB equals to 0. There are Wilson lines in this theory. Naively, you might think the Wilson lines are, you can put an arbitrary integer. It has to be an integer because A and B's are properly normalized U1 gauge fields, so they have properly quantized fluxes of Shao. But as it turns out, you can show that when n is even, this is a trivial operator. The intuitive reason is because the equation of motion, this is just a local equation of motion, but globally there's a factor of 2. So intuitively, that's making 2 times A a trivial gauge field. There's a more, you can also see it more mechanical. What does it mean that this is a trivial operator when n is even? If it's a non-trivial, if it were a non-trivial operator, we should be able to detect it in some correlation function. We should be able to compute some correlator such that the insertion of this guy makes a difference. And you can do that calculation. You can consider, you put the theory on some complicated 3 manifold, you insert different links of Wilson lines and compute this correlation function. That's what Witten did in the 80s. And you can show that when n is even, the insertion doesn't do anything. It's always a trivial operator. And intuitively, the way to do that is that you insert this guy into the path integral. What that does is to add to the action by a times some delta function. The delta function, so here I'm integrating over the 3 manifold, and the delta function has support on the locus of the insertion of this line. And here I have coefficient 2. And then you can integrate out A, and you will find that you can substitute B as delta. But since the coefficient cancel, you can show that this insertion doesn't do anything. So all that is to explain that in this theory, there's no local operator. Let me write it down, no local operator. But there are Wilson line operators, but they are all order 2. And what are the Wilson line operators? You have this guy, and this guy, and this guy. You have 4 Wilson lines in total. They are all order 2. If you square any one of them, you get identity. Why is this a Z2 gauge theory? The way to think about it is that you can think about this guy as a Z2 Wilson line. This guy is something like a magnetic line. And this is like a dionic line. And this is the right spectrum for Z2 gauge theory. Okay. So in total, we have these 4 lines. And we can talk about the spin of this Wilson line. The intuitive idea is that the Wilson lines, they are the word line of some heavy particle in some microscopic lattice model. And a heavy particle in 2 + 1D can have their little groups is the SO2. And we can talk about the SO2 spin of this heavy particle. But as you go to low energy, it's only meaningful to measure the spin modulo integer. And those integers show up in the braiding phases of all these Wilson lines. You can show that the spins are given as follows. The 3 of them are integer spins, meaning that they are boson lines. So this guy is a fermion line.
I'm sorry, I didn't understand. Why, if you go to low energy spin, you can measure only up to an integer?
So from the Tqft point of view, the reason is because now we can only measure such we can only measure this kind of braiding. And the braiding is always a phase. So if you shift the spin by integer, that doesn't affect the phase.
But for a real heavy particle, the spin is important, even if it's heavy. So it's something that, the analogy with heavy particle is not probably complete for some reason.
It's actually complete. The reason is because, yeah, in the UV, you can measure the spin as a real number, and there are heavy particles. And in the UV, the reason is because the line can end. These are like the electrons, the Ward line. And then you can measure this particle field, the spin of this particle field. But as you go to low energy, the particle is no longer there. It becomes infinitely heavy. What's left over is the defect of this Ward line. So you lose information as you go from UV to the IR. And because you lose this, so you no longer have this heavy particle as states in your Hilbert space. What you are left over are the defects that can modify your quantization. And the defects can only see the spin modulo integer. Roughly speaking, because you can always add massive degrees of freedom in your microscopic UV system. And that wouldn't affect the long distance behavior. But in the microscopic UV degrees of freedom, you can always throw in some decoupled bosons. And those bosons can dress with your anions in the UV. And that will modify the spins by integer. But those degrees of freedom will not change the long distance topological field theory.
So can you calculate the partition function of these theories?
Oh yeah, absolutely. Yeah, that's what Witten did in his paper in the 80s.
So this is the same theory as was discussed by him at that time.
Well, to be more precise, what Witten discussed was the SU2WZW model. But soon after his paper, this was generalized to arbitrary transassignments, or more precisely, Breshtakin-derived Tqft.
And you can see these anions or whatever contributing to the partition function.
Yeah, absolutely. The calculation is what I sketched earlier, that you can insert various Wilson line, and what that does is to kind of put such a term. So it's a delta function times the gauge field. And then because everything in this particular case is quadratic, you can just integrate them out. Yeah, so I mean, there's a very definitive answer if you put it on some general 3 manifold, general links between all this Wilson line, and there's a number you can compute.
Sorry, Shu-Heng, since you redrew for a second this formula that you used earlier to show the triviality of the even with the lines, I take the occasion to ask because I did not understand. If you look from the equation of motion, it would look like you get something like dB equal to the delta function. which doesn't look to allow, for instance, b equals 0. So I mean, it would look like it gives you some non-trivial b gauge field. So I did not get why the factor 2 makes it trivial.
Yeah, let me try to refresh my memory on how to do that calculation. So in that case, I can integrate out A, and I get dB equals to a delta function. And what's the next step? Well, in this case, actually, the reason is just because after I integrate out A, this solution has I can really solve B. Well, I can really solve dB in terms of delta, and there's no 1/2. If there were 2 here, if there were no 2 here, then I couldn't solve it because there's a 1/2. Let me see if I can say this better. So if I only insert one guy, then I won't get any interesting answer because that's just a vacuum expectation value of the Wilson line A. What you have to do is actually to insert 2 of them, and you have to link them somehow.
I guess okay. Maybe this is too technical to discuss now. I also didn't get why the 1/2 you cannot solve. It looks like if you have a solution for the integer, you multiply by 1/2, it solves the other one.
Yeah. Let me do that. So the real calculation you do is the following. So you have the original term, and you insert a line B. This is supported on some link. This is supported on some other link. And you ask, what's the partition function? So what is this? What does this stand for? You have some 3 manifold. You have an L. You have another L prime. Okay. And you want to compute this. So what you do is to integrate out A. I don't have any space. So you integrate out A. So then what do you get? You get B, 2B actually, equals to actually 2dB equals to delta of L prime. The D has to be taken care more carefully. But then the idea is that you can insert, okay, so what did I do? I integrate out A. So these 2 terms are gone, right? And I just plug in this solution back here. The important thing is that there's a 2. The delta L prime, the delta L here will work out to be just 1 because of the fact that they link. So what you end up having, the 2 pi will take care of itself. The important thing is that there's a factor of 2 in I pi. Oh, sorry, no, I messed it up. The important thing is that you get this. And that's a minus sign. So what that means is that if you have this link of B and this link of A, you compute this partition function, the procedure I outlined. You have to be a little bit careful about how the delta function deal with each other, but that's just geometry. You find this partition function is having nothing, but with an important minus sign.
Okay.
So that means this 2 links grades now trivially.
Okay.
However, if you put 2 here, then you get a 2 here, and then you don't get a 2 here, and therefore they grade trivially. That's why twice of that Wilson line is always a trivial operator.
Yeah, thanks a lot.
Yeah. Okay. So why do I want to talk about this Z2 gauge theory? We started with the Z2 anomaly, Z2 symmetry, 1 + 1t. What does it have to do with all that? Well, looking at this table and also the colors and the spins, it should look reminiscent of another table we encountered before. That's the table of the 4 sectors of operators in the Ising CFT. And let me put them side by side. In the Ising, we also have 4 sectors, and their spins are given by the same formula. And the physical way to understand it is that you start with the 1 + 1D Ising CFT. You couple to the Z2 gauge theory. After you couple them, what happens is that the four sectors of operators, they now live on the endpoint of this 2 + 1D annual Wilson lines. The Z2 even operators, they live at the end of the trivial line. That's easy to understand because what you did is to gauge the Z2. These guys, they are Z2 even, so they don't see anything. They are still local operators on the boundary. The Z2 odd operator, the older operator, now is attached to the Wilson line. Okay, that's natural. What's more interesting is the twisted sector state. They now carry Z2 fluxes, and they are at the end of the magnetic line in the fermion line. So this is to give a 2 + 1D interpretation of the spin selection rule that we saw earlier, which was derived from a completely 1 + 1D manner. But it actually has a 2 + 1D interpretation. So we were talking about this part of the story. What about this part? Now we have to look at this gauge theory. It's similar to the Z2 gauge theory, but now you have an additional ADA twist. This is known as the Digraph-Witten twisted Z2 gauge theory. And again, it has 4 different Wilson lines. But because of this twist, you can do the calculation that I outlined earlier. You can find that their spins are modified. There used to be 3 boson and 1 fermion, but now we have some spin 1/4 state. Oh, not state, sorry, spin 1/4 annual. And this, in the condensed matter literature, is known as the double Samuel model. Again, this table should look familiar because when we talk about an anomalous Z2, for example, in the SU2 at level 1 WZW model, there are also 4 sectors of operators, and their spins match with the spins here. And the physical picture is again that even though I cannot gauge the anomalous Z2 in 1 + 1D, I can gauge it in the when coupling to a 2 + 1D twisted Z2 gauge theory. And when I do that, each of these operators now live at the end of this annual line. All right, so that concludes the discussion of the Z2 anomaly. So let me just quickly summarize. The Lorentz spins of the twisted sector state in 1 + 1D can be shown to generally obey this spin selection rule. And recall that gauging a Z2 symmetry in 1 + 1D consists of 2 steps. Importantly, the second step is to promote some of the twisted sector states to local operators. But when Z2 is anomalous, namely in this case, there's no twisted sector state having integer spin, and this is an obstruction to gauging. The 2 + 1D SPT for the Z2 anomaly is given by this. And we can promote them to Tqft, and we see that the spins of the 1 + 1D CFT can be explained by the Wilson lines of the 2 + 1D Tqft. Okay, so that concludes the discussion of the Z2 anomaly. And I have 15 minutes, which I can talk about some other topics.
Can I ask a question?
Yeah, please.
So I guess this story, I mean, this story can also be read in the other direction, like from a more condensed matter perspective, meaning that you have some 3D condensed matter system and you would like to know which possible CFTs can live on its boundary when you cut it, and then and then you can For
Yeah,
example,
absolutely.
you know that if this condensed matter system has a certain this description that you wrote, like in terms of this Z2 gauge theory in 2+1, then you know that when you cut it, then on the boundary you should find some theory which has as a two anomaly. Is this correct? Am I reading this correctly?
What you just said is not 100% correct, and I can explain a little bit, but the spirit is absolutely correct. So, and this is a very, very interesting cultural difference. So, well, anomaly is a fascinating topic that high energy physicists and condensed matter physicists, they both like to talk about. But the way these two communities of people approach this problem is completely different. High energy physicists, we like to start with some quantum field theory. It has some global symmetry, and the global symmetry has an anomaly, and we can end there. There's an anomaly, so we cannot gauge it. We can try to do various 1+1D calculation to detect the anomaly like what I did. But alternatively, we can also characterize the anomaly by attaching a fictitious bulk to do the anomaly inflow. But the bulk isn't really there, right? The bulk is in our mind. Of course, you can say that maybe in some string theory setup, there's an actual bulk, blah, blah, blah. But from quantum field theory point of view, the bulk is imaginary. But for condensed matter physicists, it's completely the opposite. They don't start from the boundary. They start from some bulk system, some Hamiltonian lattice model with a global symmetry. And then they, as you said, cut the system with an edge and ask if there's something interesting on the edge. So they start with the bulk, while the high energy physicists usually start with the boundary. And now I can come back to your question. So first, for condensed matter physicists, and also for high energy physicists, it's important to distinguish an SPT from oh my God, there's a very bad type. Tqft. It's important to distinguish a SPT from a Tqft. If you start with an SPT in the bulk, and that's what condensed matter people typically discuss. It's some lattice model, and the low energy phase is gap with a unique ground state, but there's a non-trivial symmetry. If you have a non-trivial SPT, what that means is that the boundary cannot be trivially gapped. It has to have some degrees of freedom. Either it breaks the symmetry or there's some gapless mode. But it does not necessarily imply the boundary has to be some CFT. For example, the symmetry might be broken. If you start with the Tqft, as you said, it's not natural for them to find a CFT on the boundary. So let's look at this particular case. In the bulk, we have a Z2 gauge theory. We know the Z2 gauge theory can be coupled to the Ising just by gauging the Z2 of the Ising CFT. For high energy physicists, that's a totally natural setup. For condensed matter physicists, that's actually not natural. This is because in the Ising, there are various relevant deformations we can turn on. But generically, they allow them to be turned on, and the low energy phase is gap. So condensed matter physicists, the setup they're more interested in is that you have a Z2 gauge theory in the bulk, but the boundary is completely a gap. And such a boundary condition is allowed.
How can it be allowed in the second case when you have this twisted Z2 gauge theory where the boundary has to be anomalous?
In this case, you can also, so that's the reason why it's important to distinguish SPT versus Tqft. In this case, you can also have a gap boundary. The statement that there has to be an anomaly inflow is in the SPT picture, where the symmetry has not been gauged. If the symmetry has been gauged, it's gone. Right? We can no longer talk about its anomaly. So that's why I purposely make this two discussion into two different slides.
Okay. So just to be concrete, so you said that, for example, one SPT we could consider would be this 11 GU model.
Right, this guy.
And according to your discussion, we know that on the boundary of the Slavian GU model, we should find something interesting.
That's right.
For example, what do we find there? Do we find there CFT or do we find the broken phase?
Both could happen.
Okay.
In that particular lattice realization, I forgot exactly what they found on the edge. But this is just one particular lattice realization. There could be many other flowing to the same non-trivial SPT. And on general grounds, if you have a non-trivial SPT, the boundary, both scenarios for the boundary are possible.
Okay. While on the second slide, we would get a Kitaev model, say, and then you say Kitaev model would on the boundary just be some gap stuff and nothing interesting particularly.
So the most natural boundary for them will be a gap boundary.
Okay.
But from a high energy point of view, we usually allow ourselves to do more creative stuff.
Okay. Thanks.
Yeah. That's a very interesting question. Yeah. Actually, Zohar and Justin Cantaro, Shu-Heng, and I, we are exactly writing a paper about gap boundaries for this kind of Tqft. And let me just add one more thing since you brought this up. This theory has a Z2 global symmetry, not the Z2 gauge symmetry, not to be confused with the Z2 gauge group. But it has a Z2 global symmetry. Roughly speaking, what it does is to exchange B and A. If you impose that Z2 symmetry, then the boundary, if you preserve that Z2 symmetry and demand that the boundary doesn't break the Z2 spontaneously, then the boundary has to be gapless. So that would be the setup where icing arises naturally. You cannot just say I consider the Kitaev model in the bulk. You also have to say that you insist on a particular Z2 zero form symmetry. But anyway, that's just a side comment. Okay, so in the remaining maybe 5 minutes, I can maybe, since it's a Bootstrap collaboration, maybe let me talk about a little bit about this topic, but I didn't prepare any details. I only prepared some of the statement. So we talk a lot about anomalies in these 3 lectures. And there's a natural question in the context of Bootstrap that we can ask. We can ask, given a general, say 1 + 1D CFT with a U1 global symmetry, and let's say the CFT has central charge C, is there an upper bound on the scaling dimension of the lightest U1 charge operator? This is a question that has been discussed many times in the literature. There were a lot of nice papers, and people were interested in this question also in the context of the weak gravity conjecture in ADS. But I will not say too much about the weak gravity conjecture. Let me just pose this question as a CFT problem. This by itself doesn't have anything to do with anomaly, but in fact, the answer depends on whether the U1 symmetry in question is anomalous or not. So in the literature, using the modular Bootstrap, these 2 groups of people derive a bound as a function of C on the lightest charge operator for a holomorphic U1. For their purpose, they didn't have to distinguish an R symmetry or a capital U1 symmetry. But the point is that if you have a holomorphic U1, it's always anomalous. And that was actually the reason they can derive the bound. On the contrary, there's no bound for a non-anomalous U1. And the reason is very simple. Let's just look at the compact boson example that we have been discussed all along. At any radius R, there's a U1 momentum and a U1 winding symmetry of the free boson CFT. And there's a mixed anomaly between the 2. But the U1 momentum itself is free of anomaly, the U1 winding itself is free of anomaly, and the scaling dimension of the operators are given by this. If you look at the U1 winding symmetry, the lightest charge operator is the lightest winding operator, and its scaling dimension is given by this. This is all s equals to 1. And therefore, you can take the radius to be arbitrarily large and making the lightest charge operator arbitrarily heavy. And vice versa, if you look at just the U1 momentum symmetry, you can make the radius arbitrarily small to push your lightest charge operator to arbitrarily heavy. On the other hand, if you look at the diagonal U1, the lightest charge operator is either this guy or that guy. And then there is a bound. There is an upper bound on the lightest charge operator on this guy. So there's some connection between having an upper bound on the lightest charge operator versus whether the symmetry is anomalous or not. And this you can also show to be the case, as we did in this paper, that for any bosonic CFD with a Zn global symmetry, there is an upper bound on the lightest charge operator if and only if the Zn is anomalous. We can do that using the modular bootstrap. And recently, there's a paper here doing the same thing for fermionic CFD. So these are just some quick comments on connections to bootstrap bound. The intuition is the following. As we discussed in the beginning of this lecture, the presence of anomaly implies that certain scenario in the low energy is not possible. For example, it cannot be trivially gapped. So usually we divide the cases into, we divide the possible low energy phase into several cases. It could be symmetry breaking, it could be a Tqft, and you can see that a lot of the discussion, let me just go back to that page. A lot of the discussions in the literature, so as I said, if I have anomaly, then it cannot be trivially gapped, then we have these three possible scenarios. The second case is very much under control because it amounts to looking at all possible Tqft. The third case is also very much under control. The symmetry is just broken. But people kind of just give up on the first case. They always leave it as a side comment that, oh yeah, right, so the low energy phase can be a CFT. In CFT, you can have all kinds of crazy stuff to match the anomaly. Everything goes. Let's just leave it as a possibility there and talk about the rest. But I think what's more interesting is that actually the presence of anomaly, of course, we know that it constrains the CFT in some way. But the question is how exactly? How do you translate the anomaly data into some concrete bootstrap CFT data? In 1+1D, you can make that very precise. And that's what the references I mentioned below were doing. For example, it tells you that if you have an anomaly for the global symmetry, it means that you cannot hide the lightest charge operator to arbitrary high energy. So the presence of some light charge operator is an imprint or a consequence of the Tqft.
Question.
Yeah.
Sorry, how do you, how are you imposing the presence of the anomaly in the bootstrap? Was it by using the spin, the fact that
Yeah, using the spins, yes.
Okay.
Yeah. Thank you for that question. Yes,
Okay.
exactly. It's exactly the spin selection. Okay, so that's one topic. And I'm running out of time, but I think Slava allows me to go over time a little bit yesterday. So I'll take that liberty to do so.
Yes.
Okay, so it won't take long. I just have one more topic to talk about, which I also find interesting. So we briefly talked about this maybe in the lecture yesterday. It's a natural continuation of the 1+1D free boson discussion. So in the previous lectures, we talked about the continuum 1+1D free boson field theory. And there's a natural lattice realization. It's called the XY model. The action is given by cosine of the nearest neighbor interaction. In this model, there's only one U1, not two. We only have the U1 momentum, and the winding is not there. Only when the radius is large, we flow to the continuum field theory of the free boson, and there's an emergent winding symmetry. The phase diagram looks like this, as we discussed yesterday. For large radius, it's gapless. For small radius, it's gap. And the way to understand it is because we didn't have the winding symmetry in the UV. Therefore, we cannot forbid winding operators such as cosine phi tilde from being turned on. And if that operator is relevant, that would destabilize the whole free gapless phase, and we go to the gap phase. And indeed, the winding operator scaling dimension is proportional to R squared. So when R is very large, it's irrelevant. When R is sufficiently small, it becomes relevant, and we go to the gap phase. This is the famous BKT transition. So let's make a quick comparison between the lattice and the continuum. This is the lattice XY model. It's interacting because we have the cosine. The continuum is free, it's quadratic. On the lattice, you have only a single U1. In the continuum, you have two. On the lattice, since I have only a single U1, there's no anomaly. In the continuum, I have a mixed anomaly between the two. On the lattice, because I have a single U1, I have no exact self-duality. In the continuum, I have the exact T-duality. So the continuum free boson CFT, which features throughout the lectures, exhibits interesting emergent symmetries, dualities, and anomalies. The question is, are these phenomena exclusive to the continuum theory? Can we find them on the lattice as well? And this is some prejudice that exists in the literature for a very long time, that people always think the winding symmetry cannot be realized on the lattice. Similarly, there couldn't be such an exact T-duality on the lattice. T-duality is something that's very familiar to the high-energy physicists, but if you speak to a condensed matter physicist, it's not something that they usually think about. And the reason is precisely because in a typical lattice realization, there isn't T-duality at all. For them, the phase diagram looks like this. And it doesn't make sense to relate one R to another R because one is gapless and the other is gapped. So what I will, and finally, is typically, you usually hear people saying that anomaly cannot exist on the lattice. But we know that's not true because already in the first lecture, we talked about anomalies in quantum mechanics, which you can think about it as a lattice model. And it's still true in higher dimension. There are anomalies in the higher dimensional lattice model. In this particular context, there is actually a lattice model that flows to the free boson CFT at long distances that exhibits all these three features. In particular, this is a bosonic lattice model that realizes the U1 plus U1 anomaly. So let me quickly go over what that model looks like. So to present that model, it's useful to start with the so-called Vlan formulation of the XY model. So recall that we started with a cosine interaction. It's a standard trick to replace the cosine by a quadratic term at the price of introducing an integer gauge field. So phi used to be a circle value field, but now it's real value, but we introduce an integer gauge field. And together there's an integer gauge transformation with an integer gauge parameter k. And Vlan showed that when the radius is large, this is in the same phase as the original XY model. So intuitively, all we have done is to replace U1 by R mod Z, where R is the phi here, Z is the integer gauge field. But so far, we haven't done much. Among other things, this Vlan formulation of the XY model only has a single U1, not two. The next step is to suppress the vortices on the lattice. Because we now have an integer gauge field, we can add a field strength square to the action. And we can take the coefficient to be very large. As this coefficient becomes infinite, we can replace it by a Lagrange multiplier. So now we have this lattice model action. This is what we call the modified Vlan lattice model. This model actually has an exact momentum and an exact winding symmetry. The momentum symmetry simply shift phi, whereas the winding symmetry shift the dual field phi tilde. And the lattice model realizes the mixed anomaly between the two in exactly the same manner as in the continuum discussion. It's interesting that this modified Vlan model exhibits two Hoof anomalies between symmetries that act locally on our lattice field. Each one of them just shifts either phi or phi tilde. The anomaly is related to the fact that the local Lagrangian density, namely the summand here, they're not invariant under the U1 cross U1 symmetry. Indeed, if you shift phi tilde, this term is not invariant, but only when you sum over them, it becomes a total derivative. Because now we have the mixed Hoof anomaly already on the lattice, it means that if we impose both U1 symmetries, the phase diagram look like this. It's always the gapless free boson CFT. This is because now we can impose the winding symmetry already in the UP. And therefore, there's no BKT transition. What about T-duality? You can use the Poisson resummation applied to this integer gauge field, and with 2 lines of algebra, you can show that you can rewrite the action in terms of the dual field phi tilde with R and 1 over R exchange. Notice that in the continuum, we came a very long way to start from the original field and discover the dual field after we integrate in and integrate out a bunch of fields. On the lattice, in this modified Vlan model, it actually makes things super manifest. We have phi and phi tilde present in the action at the same time. And you can demonstrate the duality simply by doing Poisson resummation on the integer gauge field. We start with the Vlan model. We suppress the vortices to get a modified Vlan. It's also possible to go back. You can add the winding operator back in, and then that will take you back to Vlan. So it's really connected to the original Vlan. Okay, so let me just conclude. We have the original lattice XY model. It's interacting, single U1, no anomaly, no duality. However, all these features, they are present, but in this continuum field theory, we have 2 U1, we have an anomaly, we have the duality. But all these features, including the anomalies, they are not exclusive to the continuum field theory. There is actually a lattice realization for all these features. That really shows that anomalies have nothing to do with fermions. It has nothing to do with being a continuum field theory. And it's also not special to quantum mechanics, all that. Here we have a 1 + 1D bosonic lattice model that exhibits all the features. All right, I think I'll just stop here. Yeah, thank you everyone for your patience.
Thanks very much, Sam. We still have time for questions.
How sharp? Oh,
yeah. No, go ahead.
Okay, about the bound on the lightest charged operator. You said there's a bound if and only if the symmetry is anomalous. Is that a sharp statement in that bounds really can be arbitrarily high? Like the gap in the charged sector can be arbitrarily high if the symmetry is not anomalous?
Yes. And this is at least for Zn and U1, yes. Because you can always, I guess if you take a very special C, then I'm not sure. But the idea is that you can always consider the compact boson tensor product with something else, and just look at the U1 sector. Okay, let me just rephrase. The compact boson provides a counterexample to any putative bound on the lightest charge operator, and you can look at the Zn subgroup of the U1, etc.
Okay,
Right.
I think I missed that before.
Okay, yeah, but if you take a more interesting group, I have to think more about it. But at least for Zn and U1, it's manifestly the compact boson is manifestly a counterexample. I mean, of course, you can argue that this is not rigorous, because what if you take C equals to, I don't know, 1.001? Then how do I make the argument? I have to find the C equals to 0.1 CFT and tensor product with this free boson CFT to make this counterexample. And I don't know any C equals to 0.001 CFT. But I think the compact boson kind of provides a convincing counterexample. So there's some subtlety that I have to be careful about. So I was a little bit too strong in what I said.
Thanks.
I had a question, Shu-Heng, about it's a bit far away from what you discussed, but I was wondering if you have an opinion about that.
Yeah.
So so you mentioned that these anomalies, they are not exclusive to fermions, which is true. That is, you convinced us in this. Nevertheless, if you go back to say 4+1 dimensions and theories with chiral fermions, which, for example, suppose that we choose a spectrum so that there's no gauge anomaly, so we can, there's no anomaly, so that we can gauge the theory, we can actually couple those fermions to a dynamical gauge field, and everything is fine. There is an open problem of constructing a lattice realization of such models.
Right.
So since you presented this nice example of the of this winding of this model where the lattice realization of a theory was not known, of a continuum theory was not known, and yet it exists. So do you have any interesting comment to say if something similar may happen one day to this chiral gauge theories in 3+1, or is there some connection here that
So yeah, whenever people make that comment, they always start with the 1+1D example as a warm-up, and they talk about already in 1+1D, if you have a Dirac fermion, it's difficult to realize a single Dirac fermion with U1 vector and U1 axial already in 1+1D. But I don't know the exact solution to that problem, but I see a very promising direction, which I haven't got the time to work it out. So here, I gave an example of a U1 cross U1 anomaly for the C equals to 1 free boson. But the C equals to 1 free boson, as we know, can be fermionized to a Dirac fermion with third coupling. So the fermionized version of this will solve the problem in 1+1D. And the anomaly between these two U1 after fermionization becomes the anomaly of the U1 axial symmetry, the free Dirac fermion. Mm-hmm. Now the question is how to fermionize it. In the continuum, we know how to fermionize it. In the continuum, what you do is to stack with an Arf invariant, and you gauge a certain Z2. So the idea is that you tensor product with some spin invertible field theory, and you gauge some Z2. And I think there's a very straightforward thing to do on the lattice to implement that, but I haven't worked it out. And I think that's a very interesting question.
Okay, yeah, well, that's interesting.
Mm-hmm.
Thanks for the comment.
Yeah, that's very intriguing indeed.
Any other questions?
Could I ask another question about this example?
Yeah, go ahead.
So at the beginning of your lectures, you had this idea, I guess, that in the purely quantum mechanical setting, anomalies were not so different from these projective phases that you get when you have projective representations in the Hilbert space. So in this example, when you consider the anomalous lattice model, can you think of this as, can you think of this in that language? I mean, if you study this theory on a finite lattice, then you just have a pretty conventional quantum mechanical model. So is there some projective representation story underlying this mixed anomaly?
No, this anomaly cannot be thought of as projective representation, because even though even on the lattice, there's still a notion of dimensionality, right? There's still a notion of locality. So from the condensed matter point of view, when they talk about anomalies in different dimensions, they still manifest themselves in different ways. It's very special to 0+1D quantum mechanics that the anomalies are equivalent to projective representations, but not here.
But is this really so different from a 0+1 dimensional theory if I consider it on a very small periodic lattice?
Let me see. That's a good question. Well, let me just say that I don't know how to think about it as a projective representation. I don't know how to think about this anomaly as a projective representation. And I think there might be something subtle, because this is related to the comment that the reason we have such an anomaly is because the local summand is not invariant under U1 cross U1. So if you only have one site, I think there's something fishy.
Yeah, no, I would want to do it with like a handful of sites.
But then it's still different from quantum mechanics, right? What you would like to do is to really reduce it to one side, and then you can make the argument that it's just quantum mechanics. But I think in that case, some of the symmetries might become trivial. But if you have a handful of sites, then it's still different from just a 0+1D system. And then I don't see a sharp argument that it can be viewed that way.
Okay.
Thanks. Yeah, I think it's interesting. Yeah, but I think it has to do with this fact.
Yeah. Well, if there are no further questions, then I think we should thank Shu-Heng very much for his fantastic set of lectures. Thanks a lot.
Thank you. Thank you for all the interesting questions. That was really nice.
And we make a short break and see you all in 40 minutes.